Alright, this is a make-up session for the class on Monday because I forgot to turn on the streaming during the live session. So I'm just gonna repeat um, the class, without any audience. So that's gonna be a little bit odd. Alright, so the first thing about the class on Monday was we talked about the CPC, or the Central Processing Complex. The Central Processing Complex is comparable to basically just the processor and the memory and some of the peripheral chips in a modern day personal computer. Now, obviously, a personal computer doesn't have nearly as much resources as a CPC, which is a component of a mainframe computer. But it is in terms of what it contains and what it does in the entire system, it is comparable. So that is where we got to the computer motherboard, which is a term that refers to the main circuit board inside a personal computer. It is also comparable to some of the other concepts that, such as a single board computer, like the Raspberry Pi, which is a tiny little computer about 3 by 4 inches or so. It's powered by USB, and it can run Linux. To a certain point, it also compares to a system on chip, such as the Apple M1 chip. So the M1 chip is interesting because it uses a 5 nanometer process, and then the processor that we would be talking about is using a 14 nanometer process that was released in 2019. So we are really talking about Moore's law at work here because we can see how in just about 2 years, a production chip, went from 14 nanometer all the way down to 5 nanometer, and that's really some achievement. Now they come from different companies, granted, but the fabrication process, usually is there are only so many fabricators of semiconductor. I can probably name two. So, it is not about the company that designed the chip. It is about the fabricator who fabricates the chip that limits how small a transistor can be. So IBM has a lot of terms to refer to exactly the same thing. So CPC, I guess, is the current term that they officially use to refer to the processor and the memory component of a mainframe computer. But occasionally they would call it a system box, or simply a system, or a CPU. Okay, here I use single quote on one side and double quote on the other side. A CPU, which is a really old term coming from the 60s. So the whole term of CPU actually came from IBM, which stands for Central Processing Unit. And now that there are many subcomponents inside the CPU, they call it a Central Processing Complex. And then we have CEC. I did not bother to look it up, what EC stands for. But regardless of how it is called, the CPC is divided into smaller containers called drawers, which is physically a drawer too, but it is a subcomponent of the CPC, or it's the smallest physical enclosement that makes up the CPC. Each CPC drawer has its own components. It can have, with the latest mainframe, it can have up to 4 CPs. Some of the older versions can have up to 6 CPs. So I guess it depends on how big each CP is, because one CP is a integrated circuit. So if it's kind of big and takes up a lot of room, or the cooling requires a lot of room, then you can only fit so many inside a drawer, because a drawer has to be a standardized size. So a CP, which stands for Central Processor, is basically IBM's term that consumer. It's IBM's version of the consumer term of simply processor. So when people say, "Oh, I'm gonna get an Intel i7 processor in my personal computer," that is basically equivalent to what IBM refers to as a CP. So a CP is a single one CP is a single circuit board. I mean not circuit board. A single integrated circuit, otherwise called a chip. But inside this physical chip, a single CP can include multiple cores, and with the Z15 central processor, it can contain up to 12 cores in each integrated circuit. So that's really quite a lot, because if you think about the i7 Intel processor, it usually has 4, maybe 6, maybe 8 cores inside, but inside a single IBM Z15 CP there can be up to 12 independent cores. And then inside the CP we also have caches, so it has level 1 to level 3 cache inside a CP. Level 3 cache for sure is a CP. It's a shared resource for the entire CP. Level 1 cache for sure is specific to each core. I cannot remember where level 2 is. So basically, level 1 cache has the highest locality to where processing happens, and then level 3 cache, by comparison, relatively speaking, is the furthest from where processing actually happens. The rationale of having cache inside a processor, or even having cache inside a CPC, has to do with memory is usually the limitation. It's usually the threshold of how fast a CPC can operate. It's basically based on how fast it can get to memory. And that's because memory supplies not only the instructions for the CPU to execute, but also it supplies the data that the CPU needs to process, and it also stores the processed data. So you can now see, we have to feed the central processor a lot of memory content in order for it to work, and then after it works, we also have to store the result of the processing. So that's why we need to have very high speed access to memory. Unfortunately, because of memory being a off-chip resource, so that's reason number one. And then there are other additional reasons why memory cannot be accessed nearly as fast as a processor can perform its computation. So as a result, we have all these caches, which is they provide a shortcut. Okay, the best way to put it is they provide a shortcut to get to intensely accessed physical memory locations. That's actually a term that I utilized here. So without going into the actual design and circuitry and the mechanism of caches, this is the best way we can see it. It is a way to speed up the access to intensely accessed physical memory locations. Back to the central processor, IBM uses the term SCM, or single chip module, to refer to a chip like the central processor. But the SCM term is also used to refer to the next item, which is the SC, the system controller. The system controller does not really do a whole lot of processing, but it is it's a coordinator, amongst the different drawers. Okay, so it's not even a coordinator just within the central processors of the same drawer, but it also coordinates all the different processors across all of the different drawers. So the system controller offers level 4 cache. So that's what L4 stands for. It is level 4. So it's even one more step further from the level 3 cache that is inside each central processor. But level 4 cache is still fast, a fast way to access memory. And what is most interesting about the system controller is it allows communication between the drawers. So more on this later. And then inside each drawer, we also have DIMMs. DIMM stands for Dual Inline Memory Module, which basically just refers to the design of the circuit board itself. So each DIMM is a circuit board, and it carries an array of individual DRAM integrated circuits. And each MCU, which is a component inside a central processor because it's first mentioned here. An MCU is a memory control unit. Um, and as the name implies, an MCU inside a central processor is basically the you can look at it kind of like the manager. Okay, so the 12 cores inside a central processor, when they need to access memory, the central processor. I'm not sure whether I should bring this up at this point or not, but I'm going to bring it up anyway, and then maybe at some point we can kind of clarify what these things are. When a core executes instructions, it only understands logical addresses. Logical addresses is, I would say, at the least one level of abstraction away from physical memory, and sometimes it can be two levels on top of physical memory. So when a core executes an instruction and it goes, the instruction says, oh, I need to get to location 15, for instance, okay? That so-called location 15 can get translated at least once in most cases, and sometimes twice, into an actual physical location. That translation happens with the MCU. So the integral circuit to a central processor, because it sits between the 12 cores inside a central processor and the DIMMs that the central processor connects to. So this is basically it's the manager, that manages all the memory access. So as a result, how much memory a single central processor has access to is limited by how the MCU is designed. With the Z15 IBM CP, the MCU can utilize up to, not, I shouldn't say up to, it utilizes exactly 5 DIMMs, and the 5 DIMMs must have exactly the same capacity. So I will talk about this in just a little bit when we talk about how much memory can actually be used by a frame, not a single drawer, but multiple drawers connected to a collective called a frame. So more on a central processor. So a central processor has a lot of things that loosely related to the ability to remember something, but they are not really considered memory. The first part, it would be the caches. So level 1 to level 3 cache, they are really not considered a part of memory. They're considered a part of components to help access memory, but they are by themselves, they are not memory. A CP also, each core has a whole bunch of registers, but registers are not considered memory for sure, because registers they're kind of like little post-its. Okay, if you compare the content of memory as books inside a library, a register is no more than just a little post-it that people keep around in their pocket, in their purse, or in the wallet. Okay, so registers are very quick to access when we're performing computation, but they are not intended to store any type of data in any length of time. So most of the data that are stored inside registers after computation need to go back into memory at some point, and and registers basically just provide a very localized place for numbers to store, and then for the result of computation to also be stored. But the number of registers is very limited. Even in a modern architecture like the Z15, there are only so many registers. I mean, they are in double digits. Okay, which is not a whole lot. And that's why we cannot rely on registers to remember anything, because they all have to go, because there are only so many of registers inside a processor. All right. So the address space, if we think about the address space that we have talked about a lot, that does not reside in any shape or form inside a central processor. Okay, yeah, the central processor is kind of the worker, but the manual, the operations manual, that we have been using as an analogy, that is not a part of the central processor. Each core of a central processor can execute the instruction of a task independent to all of the other cores. So that means if a Z15 CP central processor, okay, I forgot about this one. So just like what I said in class, a PU, which stands for processing unit, is a more general term than a CP, which is a central processor. I know, I mean, these terms are very confusing because a processor unit or processing unit versus a central processor. I mean, what is the big difference here? So the difference is a PU, is a name that refers to anything that can do any type of processing. But a central processor is referring to a particular type of PU that is available for client applications. So a CP is basically saying, okay, I can perform operations specific to the DMV. I can perform operations that are specific to franchise tax board and so on. Whereas a PU in general does not say that because there are specialized processors that are still PUs, but they're not CPs. So these specialized processor units, they perform only system operations. So IBM says, okay, IBM as the vendor would basically say, okay, we know, what we need these PUs for, but they are not available to run any code that is coming from their clients. So that's the difference between a PU, which is a general term that refers to a particular unit that can do any type of computation, versus a CP, which is a PU, but it is available to do processing for IBM's client. So it's not a system, it's not used by the system itself, it is actually used to run client programs. So not counting the overhead of ZOS and ZVM, which is an operating system, a single Z15 CP central processor can simultaneously perform the work of 12 tasks. Now, this is actually also kind of misleading. I'm changing the terms here because I don't. A task is a better term to use here because TCB is a data structure that is used to represent a task. So it's better to use the term task here to refer to the more abstract concept instead of the data structure that represents the more abstract concept here. So as I said, this is actually misleading because IBM and also Intel, they have a technology called HyperThreading, and AMD chips have the same similar feature as well. So HyperThreading basically sort of doubles the number of tasks that you can run on a single core, quote unquote, at the same time. And the way it works is this is all complicated to explain, but I'll try my best. So inside the core, okay, so we are now not talking about single processor, we're talking about a single core inside a central processor. But inside the core, there are different ALUs and FPUs. An ALU stands for an arithmetic and logic unit, and then the FPU stands for a floating point unit. So these are subcomponents inside the core that actually get the computations done. Okay, and there are multiple of these things, but a lot of times, when one thread, I shouldn't say thread because thread is almost equivalent to a task, but a thread is used by the computer industry other than IBM. IBM never refers to the term thread, whereas in Unix and Linux, and to a certain extent Windows, they use the term thread to refer to loosely the same concept as a task in IBM terms. So task. There we go. So when the processor core is trying to perform the instruction of one particular task, it is not unusual that it cannot get the whole thing done like right away. So what it does is it will say, well, since I'm waiting for this task, this particular instruction for this task to complete, why don't I switch to another task and perform, a little bit of the operation of the other task. In other words, inside a single core, by managing, which ALU and which FPU is doing, which computation for what instruction, it can sort of multitask between two different threads of execution. So it is not truly parallel. These two tasks that are being performed are not truly parallel because they are still sharing the same set of ALUs and FPUs. So they're not truly parallel. You don't get the 2x performance that you would expect with two fully independent cores. But it would still be able to better utilize the ALUs and the FPUs inside a single core. And the percentage of improvement by using this type of hyperthreading or fake threading, or I don't know how you want to call that, but the use of this type of technology, the performance gain is largely dependent on the nature of the tasks. So if you have a compiler that is optimized to utilize this kind of hardware by analyzing the code and then generating instructions accordingly, you can get up to, I think, last time I read, about 25 to 30%, I guess, of performance gain by using this type of technology. So long story short, okay, getting back to here, I'm only using 12 here as a conservative number, but if you combine the technology that I just talked about, you can sort of call this like 14, 15 tasks or something like that. Okay, bottom line, a single CP can perform the work of 12 or more tasks at the same time. That's kind of the bottom line. Up to 4 CPs are physically located in a physical container called a drawer, and we talked about this term earlier already. So that means a single CPC drawer, because it has 4 times 12, so it can run the code corresponding to 48 tasks concurrently. 48 tasks is a lot because one job is typically one single task, and then one subsystem can also be seen as, well, okay, I shouldn't say it's one single task because it depends on the subsystem that we are talking about. In the case of DB2, DB2 by itself can be split up to a number of tasks to perform concurrent database work at the same time. So depending on how the queries, interlock with each other, that kind of limits, how many tasks actually get to run at the same time. Because just because your entire system has 1,000 tasks, doesn't mean all 1,000 tasks are ready to run. Because if a task is waiting for some I/O activity to complete, it doesn't make sense it doesn't use any type of CPC resources because it's just waiting. It's just sitting in memory and going like, okay, when the DASD is finished, moving this chunk of data into here, wake me up. Okay, so when the task is sleeping, it doesn't use CPC resources. So we are talking about 48 tasks that are ready to use CPC resources, and that is a lot. Okay, because a lot of times you might have a whole lot of tasks in your entire system, but how many of those are actually ready to do computation? Typically not a whole lot. Okay, so this is a large number already. So now we get to the SC, what the SC is doing within each drawer, the system controller. The system controller, which is a very generic term, has an interesting task. It helps to interconnect the drawers, and in one single frame, there can be up to 5 drawers. So that means, by using the SC to interconnect the 5 drawers, the CPs, 4 CPs within each drawer, and then 5 drawers having like 20 CPs, they all work together. They can basically, all 20 CPs and their associated DIMMs basically make up one single computer. And in that case, you're multiplying 48 by 5 and ending up with 240 tasks that can run concurrently using your 5 drawers, and each drawer has 4 CPs and each CP has 12 cores. And this also does not include the HyperThreading technology that I was just talking about. So realistically speaking, you're looking at, maybe 250, 260, 270 tasks that can be run concurrently. And we're only counting tasks that are ready to run. They're not waiting for I/O. They're not locking each other out. They're ready to go. Okay, so that's a pretty big number in terms of being able, how many concurrent tasks can run independently to each other. Section 2.2 talks about the memory subsystem, and the subsystem of each CP or each drawer is implemented by the DIMMs. But if we're talking about the entire subsystem, the components actually got spread around all over the place, because the DIMMs are the actual memory modules. In other words, if you want to point to a single thing inside the processor or inside the CPC and ask, where's my program? If I have a program that is running, okay, which component is holding or storing the program? That would be the DIMMs. Okay, the DIMMs are physically the stuff that is holding the data and also the program during execution. However, there are other components to help speed up the access to memory that is technically inside the DIMMs. So the system controller, which has system level 4 cache, and then the CPs, which has level 1 to level 3 cache, they are all a part of the memory subsystem. Even though the content is technically only stored in the DIMMs, the other components help to access the content quickly. The complexity, this is something that we just talked about earlier. The complexity, why it is spread all over the place. Everything, everywhere from the DIMMs to the SC, the system controller, and then we have level 3, level 1, and then level 1 cache inside the central processor. The complexity has to do with memory being the bottleneck when it comes to performance. And as a result, IBM and other vendors, okay, anyone who manufactures, computers and processor chips, they all go to these lengths in order to make sure that we can access memory as quickly as possible. So when it comes to the size of memory, we talked about how each MCU inside the processor needs 5 DIMMs to work. The 5 DIMMs has to do with the Z15 memory subsystem, managed mostly by the MCU, has built-in redundancy and self-checking. So redundancy and self-checking basically refers to the ability, so self-checking refers to the ability to detect that a memory module has gone bad. Because one of the worst things that can happen is not knowing there's a hardware fault, and basically the system continues to operate not knowing the hardware is broken. So that can be very, very bad. I have horror stories to tell in earlier days of computing about what happens when a system is not just failing, but not knowing that it is starting to fail and then continues to quote unquote operate. It does more damage than just saying I'm quitting. A component has failed, I'm just going to quit now. Okay, so self-checking is important, and that's usually done by a parity bit. But the Z15 memory subsystem also has built-in redundancy, which basically means if one DIMM has gone bad because of the self-checking mechanism, it has self-identified and go like, okay, I have just don't use me anymore. Okay, I cannot be relied on. there's built-in redundancy, which means you don't have to shut down the system, or the system doesn't have to basically quit right away, because you can still quote unquote limp along because of the redundancy until there's a convenient time to shut down the system. So this is great for maintaining uptime, because uptime is a big thing for a lot of organizations. I'm not really sure whether it is super important, for government agencies like the DMV, the Franchise Tax Board, and so on. But if you're talking about Wells Fargo Bank or Walmart or um, American Express, it is really important to keep the system up 24/7, 365. Okay, having a 1% of downtime is death to these companies. So, and that's why the redundancy is so useful, because even if a component has been identified as, okay, this one is faulty, we cannot use it anymore, there's a hot spare. Okay, this is a term that I borrow from RAID technology. It's called a hot spare. So hot spare basically means it is ready to come online and do the job in place of the component that has failed, and the system doesn't have to be shut down. Doesn't know. It's completely transparent. Okay, that whole process is completely transparent, except the system probably will get a notification in the form of an interrupt to basically say one of the memory module has gone bad. The next time you shut down the system, it's good to fix that. Um, and then when you combine this with the Type 1 hypervisor being able to move a logical partition, move an LPAR from one physical server to another physical server in a very, very short amount of time, that means you can, from the perspective of the consumer of the service, there may be zero conceivable downtime. Okay, but from the perspective of the actual frame, the actual physical box, you still have to shut it down in order to replace the faulty memory module. But from the surface perspective, if you have another box that's ready to go, you can move all the LPARs from the box that needs to be repaired to the spare box. Then you can shut down the box that needs to be repaired, and to the end users. When I use the term end users, I'm referring to anything and anyone who needs to utilize services from the LPARs. So from the perspective of the clients, they would experience close to, if not exactly, zero downtime. So that's the beauty of having redundancy, is you can defer the shutdown of the system that needs to be repaired until you have a spare box up and running, and then you move all the LPARs to the spare box, and then you can go back and shut down the one that needs to be repaired. But this comes at a price, because out of the 5 DIMMs, one does not actually contribute to the overall memory capacity of the system. So when you have 5 DIMMs, the actual available capacity is 80% of the 5 DIMMs, because technically only 4 of them are contributing to the actual memory capacity that is accessible in software. Alright, so moving on to the capacity. Okay, so this is based on 2021 technology. So obviously, if this video is ever watched in a few years, these numbers obviously would not be the same anymore. So using half a terabyte DIMMs. Okay, so these are not consumer grade DIMMs. Okay, consumer grade DIMMs, are maybe up to 16 gigs. Okay, maybe. But they are more like 4 or 8 gigs of RAM memory, DRAM per module. So using 512 gig DIMMs, each drawer can be configured to have up to 10 terabytes of total RAM, of which only 8 terabyte is available to for the software inside the drawer, running inside the drawer, because of what we said, 20% is used for redundancy. But 8 terabyte is still a large amount compared to a personal computer, which usually only have 16 gigs of RAM. And if you have a gamer system, you might have 32, maybe even 64, but it's still a very small number compared to 8 terabytes. Now, that's only for one drawer. So if you have a frame that has 4 CPC drawers, excuse me, 5 CPC drawers, then you're talking about 8 terabytes times 5, which is 40 terabytes of memory altogether. And that is a huge amount of memory by basically any standard today. All right, so now in section 2.3 talks about how LPARs fit into the picture. So an LPAR, a logical partition, is an illusion created by the PRSM. The PRSM is the actual name of the Type 1 hypervisor that IBM uses. And its full name is also, once again, it's I'm pretty sure to someone it makes sense. Processor Resource System Manager. It doesn't say anything about hypervisor, doesn't say anything about virtual machine, doesn't say anything about emulation. It just says Processor Resource System Manager. That's just amazing to me. I mean, I just, yeah. Okay. Anyway, so to an operating system like ZOS, an LPAR is a complete hardware system. So it comes with RAM, comes with the processor, comes with network controllers, comes with all the I/O channels, and so on. However, to the PRSM, which is the Type 1 hypervisor, an LPAR is really a logical construct. PRSM is also a type of software known as firmware. It still requires the processor. It can only run using the CP, but it is a firmware because it doesn't need to be loaded. Typically, when we use the word firmware, the specification of the program is not loaded from DASD or solid state drive or anything like that. It is actually, for the lack of a better word, it's baked into the system. Okay, but yet it is not immutable. You can still change it. It's just that in order to update the firmware, the process is entirely different compared to even installing ZOS on top of PRSM or anything like that. So firmware is special because when the system boots up, the firmware is the first type of program that the system runs. In the case of a personal computer, the firmware is what we call BIOS, BIOS, or these days it's UEFI. Okay, that's the firmware relative to personal computers. But in the case of a personal computer, the firmware does not perform the task of a Type 1 hypervisor. But in the case of a Z architecture, the firmware does. In the case of having PRSM, PRSM is a Type 1 hypervisor and it is loaded as a firmware in the system. So that makes it kind of interesting. But the bottom line is PRSM, using in a frame, can run a single LPAR across multiple drawers and across multiple CPs within a drawer. So in theory, you can scatter a single LPAR in terms of the memory and also in terms of the processing across a whole bunch of different components inside a frame. Now, is it a good idea? Well, it kind of depends, okay? Because each drawer has proximity to its DIMMs. So when we need to access things across different drawers, then you have to rely on the SC or the system controller to communicate so that the drawers can communicate with each other. And that becomes kind of an issue, because the level 4 cache implemented inside the SC, they're not going to be as fast as level 3 cache inside a single central processor. And as a result, you're going to have to pay a price, okay, when you have a logical partition that is spread across multiple drawers. So, but that's something that the PRSM um, management user interface software has to deal with. I tried to find information about um, how IBM potentially scatters an LPAR over multiple drawers and multiple CPs within the drawer, and what kind of algorithm it uses to determine where to put an actual LPAR, which drawer and which CP is going to run which part of an LPAR. I couldn't find any information. I'm pretty sure this is really super proprietary because this is kind of one of those secrets that makes IBM successful, right? I mean, because by being able to do this in a very efficient and well managed way, um, the client basically don't have to think about it. You don't have to think about, hey, this way of scattering a single LPAR from drawer 1 to drawer 5, using this CP over here and that CP over there, is not really giving it's not really lending itself to making the system perform well. And I mean, bottom line is this is probably a proprietary kind of thing, and that's why I couldn't find any literature on the internet that talks about it. Section 3 talks about interrupts. We talked about interrupts last week already, but this is kind of like a more formal treatment of interrupts. So a CP, even as it is now, they all in concept, okay, logically speaking, they still execute instructions sequentially, one by one. So this is despite a lot of technology to help speed things up, like pipelining, having multiple ALUs, and so on and so forth. So even though a lot of things are really happening in parallel, but from the perspective of a programmer or developer, instructions still execute sequentially, one by one. Okay, and there's actually a lot of tricks that need to be put into a processor to give the programmer the quote unquote illusion of things are actually happening sequentially when they're actually happening in parallel. Because it's difficult for a programmer to imagine all the interaction when things are truly happening in parallel. So that's why there are actually circuitries or gates and computer architecture features so that things appear to be happening sequentially. But that's the view that we're going to take in this entire discussion, because that makes it easier for people to understand what is going on and how things are managed. Section 3.1. I/O devices were the original reasons why we need interrupts. So I used an analogy yesterday about how PC-DOS uses a busy polling method to see if someone is typing something on the keyboard. And it would do the same thing with a printer. Basically a printer has an internal buffer, but once you fill up that buffer, you have to wait until the printer has printed everything from the buffer before you can feed more stuff into the buffer. And so with PC-DOS, when it's interacting with I/O devices, it will do busy polling. In other words, it does not just sit around, do something else while the printer is doing something, while the keyboard is not, when the end user is not typing anything on the keyboard. Instead, it would just keep asking those questions. Okay, it would ask keyboard controller, do you have a keystroke? Keyboard controller, do you have a keystroke? Or it will ask the printer port. Okay, back in those days we have parallel ports for printers, so it will ask the printer port and go like, okay, are you ready to take more data? Are you ready to take more data? Are you ready to take more data? Which uses up a lot of processing cycle, not for actually processing anything, but asking the same redundant question over and over again. Okay, because how fast can someone actually type on a keyboard? Not very fast. So do we really have to use like a 4.7 megahertz back in those days processor to ask that question like maybe 20,000 times a second? No, that's a waste of resources. but it was actually okay. It was okay because PC-DOS was not a multitasking or multi-threading, using today's terms, type of operating system. It can only do one thing at a time. It can only run one application at a time, and within that one single application, it can only do one thing at a time. So it was okay to use this type of method to interact with I/O devices. But on a mainframe computer, the dynamic is entirely different. So even back in the days of the IBM PC when they first came out, which is in the 1980s, even back in those days, IBM mainframe computers, they basically have a lot of jobs to run. So when one job is waiting for the DAS-D, back in those days they're still using hard drives and hard disk drives. So when one is waiting for the hard disk drive head to move from one track to the next track, um, that's a long wait. Okay, in terms of processor time, that is a long that's a long period of time. So instead of just burning, processor cycle waiting for that to happen, it would just say, hey, job number one, I see that you are waiting for the disk head to move, and that's going to take at least 20 milliseconds. So I'm just going to put you on hold, and then it will look at job 2 and say, hey, job 2 looks like you're ready to go because all the data that you need is already loaded into memory and you're ready to go. So why don't I suspend or pause job 1 and put a note and say when it's done reading from the DAS-D, you can continue, and then I'll just go ahead and work on job 2 instead. So from mainframe per computer, because we schedule so many jobs overnight, over a period of time, it kind of makes sense to switch between the different jobs. When one job is waiting for a long input-output operation, we'll just go like, okay, you just wait for the I/O operation to complete when I work on the other job. So this is multitasking, as in not the people type of multitasking, but the ability to work on different tasks by being able to switch between the tasks. So in that particular context, it doesn't make sense to wait for an input-output operation to finish because we just say, okay, you're waiting for something to finish. I will put you on hold, and then the processor wants to switch to another task to perform the computation of the other task that's ready to go. So now the question is, how do I know that the task that I just put on hold, waiting for the DAS-D to finish moving the head, how do I know that that part is done so I can go back and read a sector on that track and then continue the operation? That is when interrupts comes in handy, because an interrupt is a way for an I/O device to tell the processor and go like, hey, I just finished what you asked me to do earlier. What else do you want me to do? Okay, that is the mechanism. Now, that's not the only kind of input-output event that would cause an I/O device to request an interrupt, basically attention from the processor. Sometimes you can have exception conditions, like something bad happens. Okay, the hard drive controller says, hey, I cannot seem to move the disk head, or this particular track seems to have crashed, because I cannot find any indexing information on the track, that sort of thing. So something bad might have happened. It is also possible, in the case of a network controller, that it has received a frame. Somebody sent a frame, to a network controller. So the network controller says, okay, I know how to receive the frame, and it is now stored internal, to the network controller. But I don't understand TCP/IP. I don't understand any networking protocol. So I'm gonna get the attention of the processor, which is actually more like getting the attention of the operating system, so that I can tell the operating system and go like, okay, I just received a packet. Okay, I don't know what to do with it, but I think you know what to do with it. So why don't you, give me some attention so I can give you that packet so you can decide what to do with it. So those are all the various reasons why an input-output device might want to get the attention of quote-unquote the processor. So in terms of the hardware mechanism, an I/O device is really getting the attention of the processor. But when the processor, when it gets the attention of the processor is going to execute some instructions, right? Because that's what processors do. They execute instructions. The instructions in response to an I/O event, an input-output event, in the case of an interrupt, is actually a part of the operating system. Now, there are different names to refer to this component of an operating system. If you're using Windows, this component is called the driver, okay? And that's why when you buy a new piece of hardware, you have to load the driver. Those days are pretty much gone these days, because I guess standardization is one thing, and then the operating system can automatically identify what component has been installed so that it can go get the driver itself and you don't have to do it anymore. But before, back in the old days, when you buy a piece of hardware, it comes with a floppy disk with the quote-unquote driver in it. And the driver is basically the extra component they can add to an operating system so that the operating system knows how to interact with that I/O device. And one part of it has to do with interrupts. How do we handle the interrupts coming from that input-output device? So getting back to this paragraph here, it talks about how input-output devices or the operation of an input-output device are considered asynchronous. So the word asynchronous means it operates on its own. There's no way the program, the code running inside the computer, can predict when a hard drive is going to be done doing its thing. So that is what asynchronous means, is they are not locked in step. Synchronous means they're locked in step, and asynchronous means they're not locked in steps, which translates to unpredictable. Okay, we don't know when an operation is going to be done, or when an I/O device may require the attention of the processor / operating system. So those are the reasons why we have interrupts. In order to provide the functionality of interrupt, there are certain things inside the processor that needs to be done. Okay, and I just spotted a typo. There we go. Okay, so inside the processor, in terms of the hardware, like what you can actually see, including the pins, outside of the processor chip, an interrupt is usually implemented by at least one wire or one lead out of the processor. So when typically it is what we call an active low signal, which means when the voltage of that line is low, then it is quote-unquote active, which means in this context it means the device wants attention from the processor. And the request is also called level sensitive, which basically means as long as the processor decides to ignore this interrupt request, the I/O device will continue to make the voltage low. In other words, it will continue to request the processor's attention until the event is handled. Okay. So when the event is handled, it is up to the input-output device to release an interrupt request. So typically what that means is it will no longer hold the voltage of that pin low, and instead it will quote-unquote release it so that the voltage of the pin can be high again. So remember, this is what we call active low. That means when the voltage is low, it is quote-unquote active. It's saying yes, we need attention from the processor. And when the voltage is high, when I say high, it is all relative, but when it's not low, that's the other way to see it. It means okay, I don't need your attention anymore, we're good. When the processor is actively performing the operation of a task in an interruptible section of an address space and an interrupt is requested, then the hardware interrupt request is going to be processed. So what this sentence is saying is you can mark certain sections of an address space as uninterruptible. Okay, because software has some control over whether interrupt can happen or not. So you can basically, at the beginning of a section of code, you can say, hey, turn off all interrupts. And then at the end of that section of code, you can now say, let's re-enable interrupt. So in the section, okay, that starts with the instruction of saying, let's disable interrupts. So during the execution of that section, interrupts cannot happen. Okay, and by design, sometimes we need that to happen. We'll talk about that when we talk about serialization, but at this point, we'll just say that most of the time, um, interrupts are enabled. Okay, and so hardware interrupt can happen. So when an interrupt is requested when a program is executing in a section that is interruptible, then the hardware interrupt is going to happen and it's going to be processed because the processor says, yeah, well, I'm kind of interruptible at this point. So when the interrupt happens, the processor will do whatever it needs to surface the interrupt. The surfacing of an interrupt uses a mechanism that is almost the same as calling a subroutine, except you're not calling it from inside any program. The subroutine is also called an interrupt surface routine instead of a subroutine, and usually we just refer to it as the ISR. The ISR is called quote unquote by hardware. So you're not going to find any instruction of doing the actual call because it is actually done, it's actually triggered by the interrupt line of the processor chip being held low. Okay, so that kind of it goes back to the low level detail that we just talked about a little bit earlier. But the bottom line is there's no actual instruction calling the ISR. The result of ending up executing inside an ISR is triggered by hardware. It is not a software instruction that does that. And also, this is something that we talked about already. An interrupt is asynchronous. So the interrupted task can only say from here to here, interrupt can happen. But it cannot really predict when the interrupt is going to happen or any interrupt is going to happen within that section of code. So the next paragraph basically says, in the absence of multitasking/multithreading, when an ISR is finished, it will perform an operation similar to the returning of a normal subroutine so that the interrupted task can resume its operation completely unaware that the interrupt had occurred. So that's under the condition that there's no multitasking. When there's multitasking, when an ISR is done, when it clears the event, the input-output event, it can potentially switch to another task. So that's why I have to qualify this paragraph by saying in the absence of multithreading, because when we do have multitasking, because in the presence of multitasking, an ISR may not quote unquote return back to the interrupted task. It might actually put the interrupted task on hold because now a higher priority task can run as the result of the interrupt. So that's kind of complex, and we'll talk about this more when we talk about the dispatcher, which is in section 5. Section 3.1.2 talks about privileged access in an ISR. So the background of privileged access, has to do with most processors these days support protected operations. What that means is when you're talking about a single task running in a address space, if there's any type of error in that program and it causes something bad to happen, you want just one task or one address space to crash and needs to be fixed at some point. You don't want it to take down the entire operating system. You don't want it to take down another task, running in another address space. So you want to isolate problems of one particular address space from all of the other address spaces. But the privileged access is more than just can we mess up another address space? It also has to do with, can we access input-output devices? When I talk about input-output devices, I'm referring to the channels, which is IBM's name for the controller that controls the DASD and other devices. So we don't want a normal program to have direct access to the channels, because you don't want a random program, may not be out of bad intention, but accidentally tell a DASD to write some garbage over an existing track, because that's going to cause problems, right? Because that track may belong to a data set that this particular misbehaving program is not even accessing. So that's why we need protection. Okay, so a normal program, a normal job that is running with very low privilege level. It has limited access to memory space. It can only access its own memory space for one thing, and within that space, there are portions that it can only read. It cannot write. It cannot update or change. Just so that the program doesn't crash itself. Okay, just to make sure it doesn't crash itself in a really bad way. As a result, most programs, most of the time, the processor is running code in a low privilege level. Okay, just to be sure that when something bad happens, it is going to be very contained. That's great, right? Because it helps to isolate all the address spaces from each other. When something bad happens, it's going to be very contained. The overall system is not going to be affected. Just the one job that is misbehaving is going to crash, and then the JCL card can specify what to do when that happens. But from the perspective of an ISR, an interrupt service routine, having this restriction of access is going to be a problem, because the ISR is supposed to react or to respond to an input-output event, like the hard drive controller saying, the channel, saying, I'm done moving this chunk of data. What do you want me to do? But in order to talk to an I/O device, you need that's a higher privilege access to the hardware, to the resources in the system. So we can no longer run an ISR with restricted privileges, which also means an ISR needs to run with high privilege access. So this is why when we implement the mechanism of interrupts, this is part of what needs to go into the processor as a mechanism. Is when before we start to execute the instructions inside an ISR because of an interrupt, the privilege level has to be elevated automatically, in order so that the ISR is going to have access to the input-output device, so that it can handle everything, so that the input-output device would stop the interrupt request. When the ISR is done, and when the interrupt service routine is done, when it quote-unquote returns back to the task that the interrupted, at that point, the privilege level has to go back to whatever the task originally had. Now, if that task so happens to be a part of the operating system, is already running at a high privilege level, yeah, it's okay not to change it. But most of the time, it's going to be interrupting a user task, which means we have to return back to the low privilege level. So this automatic mechanism to change the privilege level from low to high when we get into an ISR, and it changes back to whatever it was when we return from an ISR, that is a part of the hardware specialization that has to be implemented in hardware inside the processor. So this mechanism is inside the processor itself. Section 3.1.3 talks about a special I/O device called the timer. So the timer, unlike a channel, doesn't really do any type of real input-output. Its only job is to keep track of time and then just tell the processor and go like, hey, 5 seconds has passed or 5 milliseconds has passed, and so on. So one of the tasks of a timer is to serve as a basic mechanism to track time. Because you can program, when I use the word program, it means configure, but you can configure a timer in the context of a CPC and go like, okay, I want you to give me a quote unquote tick. Basically, it's kind of like a ding, and it's just a little signal, and interrupt every 20 milliseconds, every 50 milliseconds, every 100 milliseconds. But you might say, well, sure enough, I mean, most computers, have what we call a real-time clock that actually keeps track of the real time. The real-time clock has high precision, which means when it says it is noontime, it really is exactly noontime plus or minus a tiny little fraction of a second. But it doesn't have resolution. In other words, you cannot use the real-time clock and say, how many milliseconds has passed? I don't know. I can only count in seconds. So that's why the real-time clock is not particularly useful in the context when we need the timing resolution to be in tens, possibly 100 of milliseconds, but definitely not in number of seconds. So the interrupt mechanism of a timer also helps the operating system to perform task switching, which is what the dispatcher does. We'll talk about that in section 5 probably tomorrow on Wednesday. You can also use the timer to collect data for the workload manager. Remember, the workload manager can do sampling to check, whether a particular task is actually running using processor resources or is waiting for something. So the timer provides that tick, where every single tick we can say, hey, let's go check all the tasks and see what they're doing. Which one is actually, doing processing and which one is just sitting around waiting for something. That is another use of the timer mechanism, is to collect data so that we can calculate the velocity of a particular task or of all the tasks in the context of the workload manager. All right, we are moving on to section 3.2. So section 3.2 talks about a mechanism called a software interrupt. So software interrupt refers to the mechanism of that instruction, and SVC, supervisor call, refers to what it is used for. In other words, when we refer to it as the int instruction in the context of x86, the Intel architecture, they are naming the instruction after the mechanism itself, which is a software interrupt. But when IBM names their equivalent instruction for the Z architecture and call it the SVC instruction, they are naming the instruction after its purpose. What is it used for, which is a supervisor call. All right, so let's put those two things together. Okay, why are they related? We talked about how inside an ISR, we talked about how an ISR requires privileged access to memory locations and I/O devices and other system resources. So now the question is, what if an end user job says, I want to continue to read the next portion of this data set, which is sitting on a DASD. Okay. Well, we already said the user task is not supposed to have access to the input-output devices. So that means the user task cannot directly talk to the I/O device. Now, this is not a restriction of, the user task cannot know how to operate an I/O device. It can know how to operate an I/O device. That's not a problem. It just does not have access to the I/O device. It's kind of like saying, it's just kind of saying, a normal bank customer, okay, may have access to the manual and also the map to the safe, but a normal bank customer does not have access to the safe unless escorted by a bank employee. So knowing how to operate and knowing how to do something does not mean you can do it, because you may not have access to the input-output devices to actually get a job done. Okay, so that means if a user job needs to read the next portion of a data set, it cannot actually go to the DASD and say, hey, give me the next portion of this DASD, of this data set. What is it going to do? Well, that's why we have the operating system. The operating system provides the service. So the user job basically requests a service from the operating system and say, hey, I cannot do this, but I know you can. And this is the information, this is the data set, and I would like to read from that data set that is sitting on the DASD. So the operating system, being the operating system, it is operating at a privileged level, would now actually talk to the channel and then go to the DASD, get the information in, and then it will respond back to the user job and go like, okay, here's the data of the data set that you want to access. So if you think about this interaction, there is a handoff somewhere, right? Because the user task or the user job is going to hand off the request to the operating system. Then the operating system is going to do whatever it needs in order to read from the DASD and then come back with the data of the data set. And then there's another handoff at that point where the operating system says, okay, here's the data, go do whatever you want with it, and give the data back to the user job. So that interaction is done by the SVC call instruction, which is basically a software interrupt, because it uses exactly the same mechanism that we talked about in section 3.1.2, where when an interrupt happens, right before we get into the ISR, the privilege level is increased, okay, is elevated, and then when we return from the ISR, the privilege level is back to normal. So the very same mechanism is used when we use a single instruction to trigger the ISR to execute, except in this case we don't call it an ISR because it's not actually coming from an interrupt. This time we call it a system call because we are requesting a service from the operating system. The other thing that's noteworthy also in this case is IBM uses the term supervisor to refer to the operating system. Okay. And this particular mechanism of using a software interrupt to request the operating system to do something, this is the handoff, is not unique to IBM mainframe computers. Even back in the DOS days, even in PC DOS, we talked about the PC DOS, which is the operating system of IBM PCs from the 1980s. Even DOS uses what is quote-unquote equivalent to a software interrupt, so that WordStar or some application program can ask DOS to do something for it. So and today in Windows NT and Linux and Unix, on all the different types of architecture, they all use a similar mechanism, so that an application that runs in protected mode in with a low privilege level can ask the operating system for something. So this is kind of interesting. I don't know whether it is going to be super useful for system administrators or not, but from the perspective of a system, this is kind of interesting. And I believe this is where we end in the lecture yesterday, because this is the bookmark of where I should begin on Wednesday. So I have just made up the lecture on Monday. So hopefully this is going to be useful, especially for those of you who were too tired yesterday because of the training session that ends at 4 o'clock, and then I started to talk about all of this stuff here at 5:30. Alright, so I'm going to send you guys a link